Hello everyone. This here is a video presentation on the lab test done on direct torque control. We are students from the Faculty of Electrical Engineering at University Technical Malaysia Melaka. This video is done in accordance to our task assigned for class MEKG 5143 Advanced Machine and Drive. My name is Aiman bin Abdul Qadir. I am together with my group members Ahmad Fitri bin Mazlan and Muhammad Fadli bin Abdul Aziz. The experiment is supervised by our lecturer, Dr. Auzani. Together, we have made this lab experiment possible. The content that will be shown in this video is, first, on the experimental setup used for this test. This will show the equipment used and setup done in order to run this test. Next is the test procedure done in this lab experiment. It will be separated into three parts. Part 1 is on the effect of reference torque adjustments on the torque of the motor. Part 2, which is on the effect of bandwidth adjustments on the flux of the motor. And finally, Part 3, which is on the effect of reference torque adjustments on the current components. This here is the setup and equipment used for this lab test. The main components consist of a microcontroller, an inverter, and a motor. As you can see, we have combined software and hardware elements in this setup, from small and sensitive electronic components to large motor. Now, I will further explain and show to you the experimental setup. We program and model our direct torque control using MATLAB. The model is then linked to the hardware using a control dev software provided by DSpace. It will convert the MATLAB model into a coding, which will then be used by the DSpace control board. This here is the inverter. It has 6 IGBT and a gate driver circuit. There are two purposes of a gate driver. One is to amplify the signal from the microcontroller. The gate driver will step up the voltage signal from the microcontroller in order to turn on the switch of the IGBT, since the voltage provided by the microcontroller is not sufficient for the IGBT. The second function of gate driver is to provide isolation between the electronic control circuit and the power circuit. In case of a short circuit happen at the power circuit, the sensitive electronic circuit will not be affected and is protected from damage. This board also houses two current sensors that measure the current IA and IB. We only use two since we can derive and calculate for IC since we consider the system is balanced. We use the two-phase information from IA and IB to get IC. The measured two-phase current is transferred into the ADC channel. The ADC consists of 8 channels and also another 8 channels for DAC. ADC is used to convert analog signal to digital since the current measured from the current sensor is analog. We use 2 ADC channels and 4 DAC channels. The DAC channel is connected to the oscilloscope in order to observe the output. At the power circuit side, the motor that is used in this experiment is this induction motor. This left part, which is the armature, is used to control the induction motor, while the part on the right, which is the DC generator, will act as the load. The armature is connected to the resistive band. This is the resistive band. All of its resistance is connected in parallel. This will result in it having a very low resistance, but it will still be able to handle high power. The control device that is used in this experiment is through Control Desk Flex Power software. In this software, a control has been developed where we can control the start and stop of the motor. We can also control the reference torque and hysteresis band. Other than that, we can also select which output we want to observe, either the torque, flux, or current component. In the software, it also shows the output from the oscilloscope. A webcam has also been installed in front of the motor in order to observe the movement of the motor and was displayed on the computer besides the control desk window. So, without further ado, let's proceed with the lab test.
For the first experiment, we simulate the effect of torque on the induction motor. Okay, as you can see here, TE, Tref, T-error and T-step. TE refer to the torque, Tref is the T reference, T-error is the torque error and T-stator is the torque stator. Okay, so first, okay, to simulate we need to select the torque button here in the plot selector, okay, and then we need to hit the start button here to simulate. Okay. So first, okay, right now it is zero Newton meter. Okay, as you can see here in the waveform here. Okay, the yellow line indicates the torque. The magenta line indicates the torque error, and also for the green line is the torque reference, and the blue line is the torque stator. Okay. So first, okay, this is for the 0 Newton meter, which is the motor that does not have any movement. Okay, so if we select 1 Newton meter here, okay, which is the positive part of movement, so the motor will rotate in positive direction, forward direction. So for 1 Newton meter, you can see here the movement of the motor is really slow because the step change is really low. Okay, then if we increase it to 2 Newton meter, okay, so you can see here the motor will be rotate fast. Okay, in positive direction. Next, we will simulate in the negative direction. Okay, so we try negative 1 meter. Okay, 1 meter. Okay, the simulation is really, the rotation of the motor is really slow, and you can see here in the waveform the top of the motor will be nearer to the torque error. Okay. And if we simulate negative 2 meter for 2 meter, okay, the movement of the motor will be the movement of the motor will increase because of the step change, but the movement will be in the negative direction. So that's all for the top simulation for the induction motor.
So now we are gonna explain about the second plot later, which is about the flux of the motor. We will choose the step change of 2 Newton, and the one that is important for us to adjust is the upper band and lower band. So as you can see here, since we have adjusted the upper band and lower band closer together, which is the upper band is 0.01 and the lower band is negative 0.01, we can see at the oscilloscope that the flux shape is closer to a circle. Okay, now we will raise the upper band to 0.03 and the lower band to negative 0.03. As you can see at the oscilloscope, since the distance between the upper band and lower band is much further, we can see that the shape of the flux is much more pronounced and have a zigzag shape along the circle.
Okay, now if we change the upper band and the lower band at a distance which is much higher, which is 0.05 and negative 0.05, we can see at the shape of the flux now almost resembles a hexagon, since now the distance between the upper band and lower band is much pronounced. So that's all for the flux properties of the motor. Okay, thank you.
Okay, so now we look at the last plot selector, which is the torque error and the current component A, B and C. And now I want to demonstrate when I change from 1 Newton into 2 Newtons, higher reference torque. We will demonstrate this and we can see the changes in the torque reference waveform. So I will change to 2 Newton. You can see there is a higher spike here. This indicates the changes happen during the rise of the waveform. And then I will demonstrate from 2 newtons into a lower reference torque, which is 1 newton. And you can see the waveform. Okay, here is the sudden drop of the waveform during the changes of the reference torque. And now I want to demonstrate the changes of the phase when I choose positive reference torque into negative reference torque. Okay, just now we have looked at the change of the torque error when we change from 1 Newton and into a higher torque, which is 2 Newton. And now we want to see the changes in the phase. Okay. When it is fed with positive 2 Nm, 2 Newton meter, you can see the phase here is in the sequence magenta, green and blue. And what happened when I change it into negative 2 Nm, and as I can see, the phase will change. Okay, wait. Okay, just now is a magenta, green and blue, and now we have the changes in the phase, which is blue, green and magenta. So the current component have changed in the phase.